this lesson on entropy. Entropy is a measure of randomness. That's the traditional high school definition. There's a little bit more involved definition which we're going to get to later. Another term we need to know is spontaneous. In chemistry, spontaneous doesn't mean for no reason. It means, like in common terminology, it means no external assistance is needed. If you pour two clear solutions and it turns cloudy, that would be an example of a spontaneous reaction. You pour it together and it reacts. Many, but not all, of the spontaneous reactions are exothermic. The other factor, other than the temperature or releasing heat, would be entropy. Entropy is shown by the letter S, and entropy is a measure of randomness. It's also a probability factor. You can also throw in energy required to organize. So randomness, probability, and energy to organize are three different ways of looking at this concept called entropy. What probability says is that the more variety there are, the more likely it is to occur. If you have two glass bulbs and you have 1, 2, 3, 4, 5, 6, 7, 8 particles on one side, gas particles, it is within the realm of possibility that all 8 could be on one side. On the other hand, it is much more likely to have 1, 2, 3, 4, 1, 2, 3, 4 on each side, because there's just more ways that this can happen. This way, that only one out of 2 to the 8th power can happen. This way, there's approximately half of that is over here. So there's more likely for it to be evenly separated out or random, spread out. And there are many, many ways for this to happen. Here, there's only one way. And in between is a wide range of other possibilities. So, it's not improbable, or not impossible, just highly unlikely as you go this way. More likely, more probable is as you go towards the right. Some general easy ways of understanding, if you have for solubility a gas, it's going to have a greater entropy than a liquid, and that's going to have a greater entropy than a solid. Gases, there's more locations available for it to occur, or variations. Liquid fills up the bottom, so it's that. Solids, they're locked in place, so they have very low entropy. Also, a solution would have a greater entropy than a solid, than a pure substances. Pure would probably be a better word. Solution, the two things are all mixed up, and that's why things will dissolve. Second law, thermodynamics. Thermodynamics. Spontaneous reactions increase entropy. We said that. Entropy is not conserved. You are continually in the universe becoming more and more random. It requires energy to reverse that randomness. The equation that we have is the entropy of the universe is equal to the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. And we're going to look at all three of these over the next couple lessons. If the change in entropy, delta S of the system is a positive number, the reaction is spontaneous. So spontaneous reactions increase the entropy. So if you have a positive change in entropy, it turns more spontaneous. Next, we're going to talk about temperature and entropy. If you increase the temperature, the particles move faster, and the entropy increases because there are more possible locations for the particles to be. But it also depends upon the effect depends upon the heat flow. So the surroundings. So now we're talking about the surroundings. Delta S, temperature and delta S, we're talking about delta S of the surroundings. The entropy changes in the surroundings is primarily determined by heat, determined by heat flow, both direction and size. The size of the temperature of the surroundings will make an impact on the change in entropy of the surroundings. The analogy is if you give Bill Gates $50, he's going to say, who cares? He has so much money, $50 is, pocket change. Now, if you give you $50, you're going to be dancing in the streets. You're going to celebrate because that $50 means more to you. This is completely analogous to transferring 50 kilojoules of energy to a high temperature. You're giving some energy to something that already has a lot of energy. It's going to be who cares. It's going to make less of an impact than if you give 50 kilojoules to a low temperature surrounding. So the temperature of the surroundings the lower the temperature of the surroundings, the bigger the impact the entropy will be of the transfer. If you have the sign, two things to consider here: the sign of the change in entropy of the surroundings. It gives you the direction of the heat flow. Direction of the heat flow. If it is if it's positive, it's an exothermic. So if it's an exothermic reaction, the sign is positive, so it's the opposite of what delta H would be. The other thing I consider is the size, and that depends upon the temperature, and that varies directly with heat and inversely with the temperature, the delta S. So the delta S, the size of it, directly with heat, and the heat is the amount of energy transferred, and inversely with the surrounding temperatures. So the equation, the mathematical equation for that would be delta S of the surroundings is equal to a negative delta H over T. Sample math problem: if delta H is negative 600 kilojoules and the surrounding temperature is 27 degrees Celsius, first off, you got to change it to Kelvin, so that would be 300 Kelvin. Plug that in, you get a negative 600 over 300. That makes it a positive 2 kilojoules per Kelvin. So that's the only math in this part for this section. That concludes this lesson on entropy.